Welcome to the deep dive. Today, we're going on, well, a mission, you could say. We want to unpack the hidden stories inside something that looks pretty simple, the periodic table.
Mm-hmm.
You've given us these excerpts from Periodic Table Basics, second edition, and our goal isn't just to glance at the elements. We want to dig out some surprising stuff, some insightful bits locked away in there.
Absolutely. It's amazing how much they pack into each little box on those pages.
Think of it as a shortcut, maybe, to getting a richer understanding, possibly with a few, aha moments as we figure out what this thing is really saying.
Definitely. It's way more than just symbols and numbers. You get a peek into the atom itself, the electron configuration, that's its architecture.
And its potential, right? With the oxidation states.
Exactly. How it interacts chemically, plus core properties like ionization potential and atomic weight. They tell you so much about its behavior.
Okay, let's dive into that architecture you mentioned, electron configuration. The excerpts use this shorthand, often a noble gas in brackets, right? Like radium, Ra is listed as Rn7 Spermacautsira.
Yeah.
What's that Rn telling us?
So that car, it stands for radon, is basically chemical shorthand. It means radium has the same core electrons as radon, plus those extra ones listed after the bracket.
Just 7 sevens part.
Right, 2 electrons in the 7s orbital. And what's cool is that connects directly to the table's layout. The 7, 7, 7, 7s, right? That tells you radium's in the 7th period, the 7th row down.
And the sauce.
And La Saw tells you it's in the 2nd column, the 2nd group, the alkaline earth metals. You see it elsewhere too. Look at actinium, Axi, it's Rn6d77.
It's still a 7th period because of the 7 sub.
Exactly. But the D shows it's shifted over, starting the D block elements in that period.
Okay, but then looking at some of those D block elements, things look way more complicated. Rutherfordium, RF, is Rn5 6d77. Suddenly we've got F and orbitals in there.
It gets dense.
And the number of S-less electrons isn't always 2, is it? Sometimes it's 1.
That complexity just shows the order electrons fill up the available energy levels, especially in heavier atoms. The D block and F block elements, well, they're defined by electrons going into those D and F orbitals.
Which are more complex than S and P orbitals.
Yeah, more intricate shapes, different energy levels. And the fact that the S electrons sometimes vary, maybe just one S electron, that hints at this sort of delicate energy balance inside the atom.
So maybe sometimes a slightly different arrangement is actually more stable overall.
Precisely. Like having one S electron and putting another into a D orbital might lower the total energy. And Rutherfordium having that full 5 Rio subshell, that's because the lanthanides and actinides came right before it, influencing its whole structure.
Right, and the excerpts show the lanthanides and actinides separately. We see patterns like cerium C is S46S, and the thorium TH is R-more 46s. Those NMs just change as you go across.
Exactly. The NMM represent the varying number of electrons filling those F and sometimes d orbitals. That's what gives each of those F block elements its unique identity.
So the lanthanides mostly fill the 4-4 orbitals.
Generally, yes, following that 6-4-4-6 fat pattern. The actinides are heavier, so they sometimes pop electrons into the 6d orbital too, like you see with thorium. That adds a bit more variety.
Separating them out makes sense then, visually. Highlights their unique thing.
It really does. It flags them as having these distinct electronic setups, which leads to their own particular chemistry.
Okay, let's shift gears. Oxidation states. My first thought is just, the charge an atom can have. But wow, some elements have a whole list. Nitrogen's got +3, +5, +4, +2.
Manganese is even wilder. +7, +6, +4, +2, +3.
Right. But then others, like sodium, it just says +1, calcium +2.
Yeah.
Why the huge difference? What's going on?
Well, think of those multiple states less like just charges and more like a toolbox, an element's chemical toolbox for interacting with other atoms.
A toolbox. Okay.
The oxidation state is technically the sort of hypothetical charge an atom would have if all its bonds were purely ionic. The range of states an element shows reflects how many electrons it can effectively lose, gain, or share when it bonds.
So manganese, with all those states, is like a chemical chameleon.
That's a great way to put it. It can play very different roles in compounds. Think about it, it's vital in enzymes in us, but it's also used in powerful oxidizing agents. Very versatile.
Whereas sodium, with just +1,
it has a much narrower range of interactions. Its electron setup makes it really energetically favorable to just lose that one electron. Same idea for calcium losing too. Their toolbox is smaller, more specialized.
Got it. Okay, another column here. First ionization potential. It's given in eV, electron volts. What key info does this number give us?
Ionization potential. That's fundamental. It tells you about reactivity. Specifically, it's the energy needed to pull the outermost electron completely away from a neutral atom when it's a gas.
So high energy needed means it holds on tight.
Exactly. High values, like for neon 21.57 eV, fluorine 17.42 eV, helium is way up at 24.59 eV. That tells you these elements really don't want to give up an electron. They're pretty stable as they are.
Which means they're less reactive than noble gases and halogens.
Right. Conversely, look at elements with low ionization potentials. Cesium is down at 3.89 EV, rubidium at 4.18 EV.
Tiny numbers comparatively.
Very low. They give up that outer electron easily. That makes them super reactive metals. And it's fascinating. That abstract number translates directly to real-world behavior. Cesium's willingness to lose an electron, that's actually used in atomic clocks for incredibly precise timing.
Huh. Interesting connection. Okay, now, atomic weight. This always felt pretty straightforward to me. It's just how much an atom weighs, right?
Yeah.
But then there's this other table in the excerpt showing percent natural abundance of isotopes. Like carbon-12 is 98.9%, but carbon-13 is 1.1%. How do these fit together?
Yeah, that's a common point of confusion. The atomic weight you see on the main table isn't actually the weight of one specific atom. Most elements you see exist naturally as a mix of isotopes. Same number of protons, so it's the same element, but different numbers of neutrons, meaning slightly different masses.
So the atomic weight is an average?
A weighted average, precisely. It takes the mass of each naturally occurring isotope and weights it by how common it is, its natural abundance.
So looking back at the examples, manganese has an atomic weight of 54.94. The abundance table says it's pretty much 100% manganese 55.
Right. So its average weight is very close to the mass of that one dominant isotope.
But tin, with an atomic weight of 118.7, the abundance table lists, wow, like 10 different isotopes.
Exactly. So that 1 in 18.7 is the weighted average of all those different tin isotopes, reflecting how much of each you'd find in a natural sample. It's a reminder that even that single number represents this complex isotopic reality out there.
And then we hit elements marked synthetic. Towards the heavy end of the table, promethium, technetium, neptunium, plutonium, all the way down.
Lots of them.
What does synthetic mean for their isotopes and atomic weight?
Synthetic just means they aren't really found naturally on Earth in any significant amount. We make them in labs, usually through nuclear reactions.
Right.
And because they're often really unstable, they decay radioactively pretty fast. So they don't have stable, naturally occurring isotopes that contribute to a standard atomic weight, like, say, carbon or tin do.
So the weight listed for them is?
It usually refers to the mass number of the most stable isotope known, or perhaps the one that's most commonly produced. It basically flags their artificial origin and often their short lifespan.
The table also gives us glimpses into the physical world. State at standard temperature and pressure, solid, liquid, gas, that's familiar. Aluminum solid, bromine liquid, neon gas.
Standard stuff, yeah.
But then there's crystal structures, FCC, BCC, hex, rhomb, tetra, a whole alphabet soup. What do these codes tell us about the elements?
So the state tells you how the atoms generally behave under normal conditions. Loose as a gas, flowing as a liquid, fixed as a solid. The crystal structure tells you how the atoms arrange themselves when they're in that solid state.
How they pack together.
Exactly. Think of stacking tiny spheres. You can do it in different ways, right? Some ways pack them tighter, some create different symmetries. FCC means face-centered cubic, like atoms at the corners in the middle of each face of a cube. Aluminum does that.
Okay, and BCC?
Body-centered cubic, atoms at the corners and one right in the middle. Cesium does that. Zinc uses hex, a hexagonal pattern. These different atomic blueprints, these structures, directly influence the element's big-picture properties.
Like hardness, density?
Precisely. Density, hardness, how well it conducts electricity. It all connects back to how those atoms are fundamentally arranged in the solid. Shows the amazing variety in how basic building blocks can organize.
We also see elemental abundance, milligrams per kilogram in the Earth's crust. And the differences are huge. Aluminum is way up there, 82,300 milligram kilograms. Others are tiny amounts. What's the story there?
Yeah, the range is vast. That abundance data basically tells you about the recipe for the Earth's crust, its outer layer.
Where do the differences come from?
It reflects a couple of things. First, the nuclear reactions inside stars, long before our solar system even formed. That's what created the elements in the first place, in different amounts. Second, geological processes here on Earth have concentrated some elements and dispersed others.
So abundant ones like aluminum and silicon are just common in rocks.
Very common, yeah.
Yeah.
They form the basis of many minerals. Rarer elements might have formed less often in stars, or maybe they only get concentrated in very specific geological settings. Understanding this is key for geology, finding resources, even understanding life, since some trace elements are essential.
And I noticed right near the bottom for some of the really heavy elements, like Rutherfordium onwards, there's this disk note, followed by a year and often a place. Dubna, Russia; Berkeley, California; Darmstadt, Germany.
Yes, the discovery notes.
It's like a little timestamp, a mini history lesson right there.
Yeah, it is. It marks when and where these artificial elements were first created and identified. It's such a cool reminder that science isn't static, right? We're still discovering, still pushing the edges of what we know about matter,
And it points to specific labs and places.
which highlights the massive effort and technology needed to make and find these super heavy elements. Often requires huge facilities, international collaboration. It speaks volumes about modern science.
And finally, the excerpts even throw in fundamental constants and conversion factors. Avogadro's number, Planck's constant speed of light, temperature scales.
The essentials.
It almost feels like the periodic table is sort of the central switchboard connecting everything in science.
That's a perfect analogy.
Yeah.
Including those constants emphasizes that the table isn't just some isolated chemistry chart. It's deeply tied into the fundamental laws of physics and chemistry governing everything.
They provide the links.
Exactly. Those constants are the numerical bridges between the tiny world of atoms we can't see and the macroscopic world we experience. They let us make calculations, predictions, understand why elements behave the way they do based on those underlying universal rules.
So pulling it all together then, it's really clear this chart, even from a basic guide, is incredibly dense. It's not just a list.
Not all.
It hints at complex electron structures, vastly different chemical personalities through oxidation states, how reactive things are via ionization potential.
The reality of isotopes hidden in atomic weights, the different physical forms matter takes, even the history of discovery.
It's all packed in there.
Absolutely. This kind of deep dive really does give you a shortcut, I think, to appreciating just how profound and interconnected this cornerstone of science is.
It's way more than a catalog. It feels more like a key to understanding the building blocks of, well, everything.
Couldn't agree more. It unlocks so much about the universe and the rules it runs by.
Makes you wonder, doesn't it? Considering how much information is layered into this single chart, what other hidden stories, what other deep narratives about the universe might be hiding in plain sight in other sets of seemingly simple data?
That's a great question to ponder.
Definitely encourages you to look again, maybe with fresh eyes, at information you thought you knew. Thanks for joining us on this deep dive.